Hi everyone, welcome to our first video. So in this video we are going to discuss how to identify glomeruli in human kidney tissue images using advanced machine learning or deep learning techniques. So basically what is a glomeruli? Well, according to Google, glomeruli are the tiny network of blood vessels that are the cleaning units of your kidney. They filter waste and remove extra fluids from your blood. When glomeruli are damaged and can't function as they should, it's called glomerular disease. Many diseases and conditions can damage the glomeruli. I think enough background information and we can move to data now. So the dataset contains bunch of TIFF files. A TIFF, which stands for Tag Image File Format, is a computer file used to store raster graphics and image information, which is very favorite among photographers. TIFFs are a handy way to storing high quality images before editing if you want to avoid lossy file formats. One possible question might be that why not JPG? A TIFF will enable you to store richer, more detailed images. It's good practice to save your original or source photos as TIFF files. The data we are dealing with contains many important informations which should be preserved well. The annotations, which basically the masks, are provided as the RLE encoded format as well as the unencoded JSON forms. Run length encoding (RLE) is a form of lossless data compression in which runs of data, sequences in which the same data value occurs in many consecutive data elements, are stored as a single data value in count, rather than as the original run. So here is what I'm trying to say: when we have data with a lot of repeats, we can shift them to RLE encoded, aka frequency data pair. Here is an example of RLE encoded data. And for the JSON files, they contains bunch of informations like polygons, properties, etc. But our solution won't be focusing on that, we will be working with RLE files. And all of the data is from a Kaggle competition, HubMap Hacking the Kidney, which is organized by Innovation Digi. I will attach all the links in description. So I think that was a good to go introduction of data. We will see some more visuals in next section. We are solving an image segmentation problem where we are given images and their masks. So here is a sample of data we are with. These are basically the fresh, frozen and formalin fixed paraffin embedded FFPE pass kidney images. Don't worry if you don't know what that means, simply understand them as kidney images. And talking about what we are predicting, here is what we are expect to predict: the mask of glomeruli in kidney. So the mask which we just saw is a small piece of this complete picture, so you can imagine how big those TIFF files are. They are in gigabytes. Look at the dimensions on X and Y axis. Of course, dealing with such high dimensions is not possible with limited resources, so we have a method to deal with them which we are going to discuss in next section. This is the RLE format which is given to us for each of the file. So all of these amazing visualizations are taken from this notebook. I will attach the link in description. I hope you understood the problem statement and the data, and I believe we can move towards the data preparation part. Before starting, let me mention that the methodology we are studying onwards from this section is almost from this winning solution of this competition, and I will recommend you to read the solution on your own. I will attach the link in description. So moving forward, you remember that the given data is very huge in size. Talking about only one file, it's in gigabytes. So how are we going to fit this much data in our RAM and training it? That will take ages. So there is the styling technique. So basically the idea is we take a big file like in thousands of dimensions and we break it down into some untiles. This is very simple and effective technique. You are taking a big picture and generating small number of pictures from it. Now data will contain each image with its corresponding mask, that too in a very limited dimensions. For our solution, we are having 1024 by 1024 dimensions, so it's easier to fit into memory. So we go a step further into the balanced tile sampling. So basically it's same as the tiling defined before. We generate some tiles, but here we are post-processing it further. We are dividing the data into several bins. So these bins will tell us if the particular image or tile contains one or two or n number of masks or no mask at all. We are doing this to use this useful information in our modeling part. Along with some basic augmentations like rotating, scaling, etc., we also did a very simple custom augmentation where we shifted the tiles by half of their sizes, and this additional generated data proved to be useful for the model. So the model, instead of memorizing the glomeruli in center, will consider finding it in other locations as well, and as they are shifted half of the size of image, the masks might also be shifted or maybe half preserved, enabling our model to learn a robust representation of those masks. So basically that is it from this video. This was the first part where we understood the data problem in the preparation, and in next video we will be moving forward with modeling part. If you like these type of informative videos in the area of data science and artificial intelligence, please consider subscribing. Thanks.